Hello, good afternoon, everyone. Thank you all for joining us for another USALCO webinar, which will be available on Apple Podcasts and on our USALCO YouTube channel after this airs today. I'll begin today by introducing myself. My name is Chris Lacey, and I'm located in New Braunfels, Texas, near San Antonio. I joined USALCO in 2017 in a technical commercial role, and I'm now serving as a technical marketing manager for the past year and a half or so. On the podcast, we also have Brian Leota, who is located in the San Francisco Bay Area. Brian joined USALCO in 2022 and serves as our Director of Marketing and Product Development now. He came to USALCO from Brentag, North America's water treatment business, where he served there for over 20 years. And then finally, our speaker for today is Chris Tesone. Chris has been with USALCO for over 17 years. Prior to USALCO, Chris spent 19 years in industrial water treatment at Betts Laboratories. Chris is serving as our Director of Sales for the North now, and after he joined USALCO, he began working in the field implementing various types of coagulant programs for phosphorus removal, such as aluminum sulfate, sodium aluminate, and polyaluminum chloride programs. So now we'll go ahead and hand over to Brian Leota. We'll now introduce USALCO for those not already familiar.
Thanks, Chris. So this illustration just generally shows the critical aspects of a very typical drinking water facility: coagulation, filtration, pH control, disinfection, chemical process control, and operating personnel, all essential to providing clean water. USALCO offers an industry-leading coagulant portfolio and a variety of services that improve filter performance, automated coagulant dosing, which is our co-pilot system, and we provide expert support and training, such as the USALCO Coagulant Academy, for example. All of these offerings maximize facility production, they reduce maintenance and energy costs, lower sludge disposal, pH control, etc., and minimize carbon emissions, ultimately enhancing the resiliency and efficiency of the entire process. As far as our product line goes, we offer a diverse range of advanced coagulants and polymers tailored to optimize water treatment processes. Our signature brands like Delpak, UltraPak, GPak, DeltaFloc, and UltraFloc provide specialized solutions for various treatment needs. For iron and aluminum specifically, we manufacture a pretty comprehensive range, including all sorts of packs and iron salts designed to enhance coagulation, reduce sludge, and improve water clarity. And our polymers, like the polydadmax and epis, offer additional tools to support efficient coagulation and liquid-solid separation. And just to add a final comment before I turn things over to our other presenters, our product line is really infinitely customizable, and we take this approach to water treatment recognizing that every water system has attributes that make it unique. So ours is not a one-size-fits-all approach. We take a consultative view on each and every opportunity. And with that, I'm going to hand it over to Chris.
All right. Oh, here just a moment. Let me get this back. There we are. So for today's event, please email any questions you have to webinar@usalco.com. If you have any other requests, if you need a copy of the deck or anything, and this deck will be available at the end. If you need any help finding anything, just let us know there. And I'm going to go ahead and cover the agenda real quick. So we're going to be covering nutrient removal today. We're going to be covering the definition of phosphorus and different types. We're going to be covering biological and chemical removal, as well as the mechanism of those reactions. And then the difference between Al and Fe, so aluminum and iron. We're going to cover the key considerations and chemical removal, and then the typical coagulants used, and as well as bench testing and dosage calculations. Now I'll go ahead and hand this over to Chris now to go ahead and take over.
Thank you, Chris. It's good to be with you today. And as Chris indicated, we want to share with you various aspects of phosphorus and phosphorus removal and coagulant technologies that are used, how to basically evaluate a phosphorus removal plan, and along the way also share some of the things that I've learned over the years that I've experienced specifically with regard to phosphorus removal. So just, starting with some of the basics, most of your muni wastewater plants are return activated sludge plants. And this is basically just a diagram depicting that. Now you'll see you'll see this arrow showing the primary or preferred chemical feed point. Now, that's not to say that there are municipalities that are utilizing alternate feed points, whether it's after the influent or after the primary clarifier. Some facilities actually use more than one feed point. And we'll elaborate a little more on this later. But the gist of it is typically the preferred feed point is after aeration and before secondary clarification, because you really want the treatment process to remove any insoluble phosphorus and or soluble phosphorus if there's any BioP uptake, and really focus the coagulant as a polishing agent. Typically in a wastewater plant, and the goals are phosphorus removal, improved settling rate. Is there an alkalinity impact? And if there is, try to minimize that. Always looking at sludge. Can you reduce the amount of sludge? And then overall clarification. And this is more applicable in industrial applications rather than municipal, where you're looking at BOD, COD, FOG, in addition to phosphorus. Phosphorus, it's a little more complicated. And one of the things that I always ask in working with municipalities or industrial customers, especially municipalities, is, what are your goals? Is it strictly phosphorus removal, or are you also looking for something that's going to help, settling in your final clarifiers? Are you having any struggles with alkalinity? Are you using caustic or lime to boost that alkalinity, et cetera? So as you kind of do a people and a technical survey, those are some of the questions that you should typically ask.
And Chris, can I ask for that? So what I think I'm hearing is that municipals primarily use coagulants for phosphorus removal, whereas industrial users will use them for a variety of reasons.
Yes. I mean, it's just a more complex wastewater. Municipal wastewater, not to say, and we'll get into this later as far as, the characteristics of a municipal water influence, whether it's strictly residential, commercial, or if there's some industrial, that makes a difference as far as maybe your approach in the coagulant technology that you would use. But for the most part, my experience, municipalities are strictly looking at just pee removal. That's a great question, but you really need, again, you need to ask the questions because there are some coagulants that are better in settling than others, even though they all may be effective to a certain degree with phosphorus removal. So why is there a need to remove phosphorus? And essentially, nitrogen and phosphorus are essential nutrients for aquatic plant growth. And if there's too much nitrogen and phosphorus, a body of water can become what they call eutrophic, where you could have excess algae growth, depleted oxygen to sustain fish, unsightly odors, also potential toxins, microcystin. I think maybe folks on this call are aware of the problem that Toledo had, or the Toledo water plant was shut down a few years back because of a serious algal bloom in the western basin of Lake Erie. Algae growth is also limited by the least available nutrient, which is phosphorus. Now, one of the developments, I believe it was probably 5 or 6 years ago, there was a study out that basically said that nitrogen, it really should not be too concerned, a wastewater plant be too concerned with removal of nitrogen, because algae can fix atmospheric nitrogen on their own. So really, trying to reduce the amount of nitrogen discharged to a body of water really didn't matter. And it really, the focus has to be on phosphorus. When people think of phosphorus, maybe just to kind of clearly define what it is and what it isn't. Pure elemental phosphorus is rare. Usually, typically, phosphorus exists as a part of a phosphate molecule, and it can be organic or inorganic. organic phosphate obviously has a carbon-based molecule associated with it, and it's in both plant and or animal tissue. Phosphate that's not associated with organic materials, obviously inorganic, and that form is required by plants. However, animals can use either organic or inorganic phosphate. And both of those types can either be dissolved or suspended in water. And that's an important point between soluble and insoluble phosphorus that we'll touch upon as we go through the presentation. Some operational definitions, most people know or measure total phosphate or orthophosphate. Orthophosphate is mostly dissolved and highly reactive, where you've got acid hydrolyzable phosphate, which is polyphosphates, metaphosphates that are somewhat reactive. And then you have, I don't know if you would say they're exotic phosphates, but phospholipids, nucleotides, et cetera, which are mostly particulate but less reactive. And when we talk about reactive, we mean readily removable, that will readily react with a metal salt to facilitate removal. So what this is saying is the hydrolyzable types of phosphorus or phosphate are very not completely removable, and the acid hydrolyzable we really can't remove. But for the most part, in a municipal application, most of your phosphorus that's coming into the plant is highly reactive. This is a bit of a busy slide, but it really illustrates that there is a phosphorus cycle, and between uptake of phosphorus by animals, which return through the waste, return to the soil, and then that phosphorus is available through reactions to be plants can uptake that. So it's a cycle between a plant life and animal life of phosphorus in various forms. Monitoring phosphorus, there's the total orthophosphate test. There's the total phosphorus, dissolved phosphorus. And I guess the point in all this is that, and we'll touch on this later when we talk about bench testing, is that the EPA really, or the regulatory agencies, measure total phosphorus. So they really have no concern of whether that's phosphorus in their effluent is soluble or insoluble. But it's important that we know that to be able to solve problems, but also to be able to do benchline or baseline bench testing, because really the focus of the coagulants is the reduction of soluble phosphorus and creating an insoluble material that's easily settled. Phosphorus removal, and maybe this is a bit of a dated slide. It talks about the EPA mandating phosphorus in plant effluent. And that's still true, but my experience over the years has been that the federal EPA has kind of turned this over to the states. And restrictions do increase over time, but not as quickly as I anticipated 5-10 years ago. More and more municipalities are getting P limits, but it just seems like it's not the magnitude that one would expect. Now, given that, there are certain areas of the country, such as the Chesapeake Bay region, that have phosphorus limits and have had phosphorus limits for a number of years. I mean, really, the government, the regulatory agencies started paying attention to phosphorus in the late 60s, early 70s, with the advent of the Clean Water Act and also the Great Lakes Water Agreement in 1978. So there was a realization and more of a focus on phosphorus removal and why it needed to be addressed. But you think it'd be more widespread. But as an example here, I live in Ohio, Northeast Ohio, and essentially, if you draw a line across the state, the top third of the state is part of the Lake Erie watershed. So that's covered with the Great Lakes Water Agreement. So all of those wastewater plants have a limit. Below that, 2/3 of the state, it's really dependent on where each plant is located and what body of water they're discharging to. And we started to see some increase in plants getting limits, especially in the Little Miami area and western Ohio. Another example is the state of Indiana, which is kind of it has a unique position on this. I mean, every wastewater plant in the state of Indiana has a phosphorus limit. And that was that came about with the incident I just mentioned in Toledo, because that northeastern Indiana, a lot of those farmlands and wastewater treatment plants ultimately go into the Lake Erie watershed. So every plant in Indiana now has a phosphorus limit. At the time, the edict was when your permit was coming up for renewal, you are going to get a limit. And USALCO has been, intimately involved in that market and helping and assisting those plants with their compliance. We talk about technologies, I mean, biological and chemical, and Brian and I were speaking of this earlier. I've run into over the years very few plants that have strictly biological pea removal. A couple reasons. Number one, you have to have certain nutrients and certain characteristics of your influent water, and that has to be consistent. And number two, it's one plant may have diop removal, and let's try this down the road, and it doesn't work because it really is specific to the influent. So I don't see many plants with biological removal. I do see some that may go back and forth or use chemicals to supplement the removal of phosphorus. For the longest time, it was anticipated that the reaction of a metal salt was known, I think, or believed that the reaction of a metal salt with phosphorus was strictly a precipitation reaction. And and Chris has referenced where this information came from on the lower right here, but really it's the reaction of the metal salt with the natural alkalinity in the water to form what they call an HMO. It's not a health maintenance organization, but a hydrous metal oxide. And essentially what that'll do is it'll absorb, the soluble P will absorb to the HMO reactive sites. And you also get like a co-precipitation where that hydrous metal oxide will enmesh the insoluble phosphorus and the particulate phosphorus. And the next slide, I think, does a really good job of kind of depicting that. And thus, it's really important that you implement your coagulant at a point of good mixing to optimize the efficiency of your chemical dosage. So, when you look at a typical wastewater plant, usually you'll see 2 to 6 ppm of phosphorus in the influent. And largely that's residential. You may have some light industrial, and you can see here, if you have a food or metal processing plant, you could get higher levels of phosphorus, much higher, and they could be somewhat inconsistent depending on the process associated with that industrial discharger. One of the things that I recall in industrial a discharger, there was a plant in Indiana which basically was taking phosphorus-laden waste from a meat packing plant into the municipal wastewater treatment plant. It was in Indiana. They'd just gotten their limit, and they were getting probably 16 to 20 ppm. And they started off using alum, and they just couldn't meet their limit. They went to polyaluminum chloride, couldn't meet their limit. And then, we got involved and took a look at things. And what we found out was that the reason they were feeding enough, but they were overfeeding the coagulant so much that it was destabilizing the flock. And what was going out the door was both more insoluble phosphorus than soluble phosphorus. So it was just too much for that particular coagulants to handle. So we went in with and looked at sodium aluminate, which has probably the second highest aluminum content of all aluminum coagulants, and it worked very well. one of the reasons is it's not a very good coagulant. It doesn't really form too much of a flock. But in this instance, it solved the problem. They were able to get into compliance. So I guess the moral of the story is understanding, your influent, understanding the treatment process in the plant goes a long way into really making sure that you have the correct coagulant technology. And again, I stated this earlier, that it's really important to allow the treatment process to remove as much of the phosphorus as it can and use the coagulant as a polishing agent. Oh, sorry about that. Okay, so some of the typical coagulants used for phosphorus removal are aluminum chloride, aluminum sulfate, polyaluminum chloride, of which ACH would be included in that category, sodium aluminate, which I just referenced, and also ferric and ferrous chloride and ferric and ferrous sulfate. Now, there is a big difference in aluminum versus iron, and I'm sure all of you have heard of or aware that iron can negatively affect UV disinfection. And this is something that it's no secret. This is something that some of the major UV manufacturers like Trojan will readily advise in their literature that you could get staining of bulbs, et cetera. And my experience has been, depending on the superintendent, sometimes it's a big deal. Usually it's not a big deal. But it is true that iron can interfere with the disinfection, if you will, that because it's absorbed onto suspended solids and bacterial flock and can prevent UV light from getting to those target microorganisms. And essentially, with UV systems, you can, and I've done trials and I've seen this, you can run your UV system at a lower rate. So there's some energy savings because of better transmission. Another difference between aluminum and iron is that the aluminum molecule weighs less than half of what the iron molecule. So you really have twice as many molecules in a pound of any, this is LSA, a pound of any aluminum-based coagulant as opposed to an iron-based coagulant. And another key aspect, although I've only seen it once in my career, is that iron will under anoxic conditions will release phosphorus, whereas aluminum, once that HMO basically absorbs and traps that phosphorus, it does not let it go. I saw this years ago at a trial in Western Ohio where it was a college town and their flows were much lower in the summer, and they just let their sludge get too old. And I think they were running one more final clarifier than they really should have been running. And all of a sudden they start spiking phosphorus, and they had more phosphorus going out the door than they had coming in. And what we determined was exactly what I just described, is that the iron, they were using ferrous chloride. The iron was releasing the phosphorus. This is a little busy chart, but it's a very important one. What it really depicts is not only the the metal content in each type of coagulant, but also what it's saying is, for every ppm of product you feed, well, let me rephrase that. Let's say for Delpac 1842. For every ppm you feed, you will need 0.232 ppm of sodium hydroxide to restore the alkalinity that you've consumed. Now, as you can see, if you go down to the iron salts, ferric and ferric chloride have pretty much the highest alkalinity consumption per ppm of any of these coagulants. Another aspect that's not depicted here is the basicity of the various aluminum coagulants. What I have found, with ACH, obviously it has the highest basicity at 83%, also has the highest aluminum oxide content at 23. So you think, wow, that's the most concentrated product. We should use that. Well, and we'll talk about it when we go through the bench testing, but what I have found is in municipal water treatment, wastewater treatment, the higher the basicity, the less effective the coagulant is in phosphorus removal. So typically your lower to mid range basicity products will work better, even though the aluminum content's slightly lower. You will get a much more, you'll have a much more lower molar ratio. It'll be much more efficient than say the higher basicities. I can't explain why, but that's basically, time and time again what we discover. Now, if you're looking at an industrial application, as we talked earlier, where you've got fats, oils, and greases, and BOD, and things other than phosphorus, or in addition to phosphorus, I should say, then like ACH and those higher basicity coagulants really work better than, say, the lower to medium basicity coagulants. So, before you spin jar one, I talked earlier about doing a people survey of what the plant's objectives are and doing a technical survey. And part of that is understanding the raw water sources, the types, the fluctuations. Do they have industrial dischargers where, at midnight, a change of shift or something, their wastewater, the industrial concerns wastewater changes. Also, do you have some side stream contributors? If you've got a filter press, how often are you pressing? How often are you returning filtrate to the head of the plant? And again, another question you always ask is, do you just have a need for phosphorus removal, or can we help with settling? And as you get into bench testing, you want to evaluate the products based on a metal to phosphorus ratio, the best performers at the lowest ratio. And my experience, most plants are in that 2-to-1 ratio, meaning it's going to take two pounds of aluminum for every pound of phosphorus that needs to be removed. Now, I've seen some plants, I think the best I've seen, it's been around 1 or slightly 1, but that's kind of rare. So, and we'll talk about in bench testing where to start. But one of the other things to keep in mind is that it's been proven that any phosphorus concentration below, say, 0.3 ppm, the molar ratio increases dramatically, meaning you're going to need much, much more of the metal salt to remove phosphorus, or to get the phosphorus below 0.3 ppm. That seems to be the cutoff point where it just really spikes. So if you're in Wisconsin and you've got a plant that has a technology-based limit, and I've seen limits up there like 0.07, 0.05, not to say that the aluminum or iron won't work, but be mindful of the 0.3 ppm, because below that, your dosages really, really spike up. And there are some other ways you can address that with some other products out there once you're below 0.3 ppm. Feed point and mixing are key. Another important point is that some folks do feed at the head of the plant, or have 2 feed points. The issue with that is you will get other constituents in the raw water at the head of the plant that will compete with the phosphorus for the aluminum. So typically your molar ratios at the headworks are going to be higher than they are if you're testing, right before secondary clarification. Other things to look at, impact of chemical and or effluent pH and system alkalinity, ammonia removal, sludge to water, and we talked a little bit about that, UV. Reviewing systems for compatibility design around the best coagulant. What about their storage and handling? Does the coagulant tend to have different coagulants? We have different freeze points, different crystallization points. Where are the tanks located? How long are the feed lines? Also, the final clarification as it pertains to solid settling, and also monitoring and control. How are they, or how will you, or how are they distributing the coagulant? What is their control protocol? How frequently are they testing? Is it is the feed flow paced? Is it just base fed, etc.? Now getting to the fun part of jar testing. So again, we're focused on phosphorus removal. We're looking at the molar ratio when we test, and everything's, various coagulants, various aluminum concentrations, but you want to test them on an equal metal basis at various ratios. So if you've got a higher concentration, one coagulants or one aluminum coagulant's higher in concentration than the other, both at a 2-to-1 ratio, obviously the higher concentration chemical will have a lower dosage requirement. Sample point is critical, and this kind of goes back to what I just said about the headworks. So you go into a plant, you're going to do jar tests, and let's say they're already using another coagulant, iron or whatnot. So the challenge becomes, well, if I take my sample post aeration, how much of that particular coagulant iron do I have in there? So oftentimes what I would do is I'll test prior to the addition of any coagulant. I'll test after the screen, test the influent, but I'll test the aluminum coagulants, but also test the incumbent coagulant, typically would be iron, because it's not going to be efficient at that point. So you want to basically look at what they're currently doing, you test their current coagulant and the other coagulants you're going to try to kind of put everything on equal footing, understanding that the molar ratio is going to be higher when you're treating a dirtier water, but it's very difficult, if not impossible, to predict how much higher.
And Chris, I have a question. Do you typically metal balance when you're jar testing?
I think that's what the molar ratio does. That's what that's what essentially metal balancing. Yeah.
Got it.
So to start, once you determine your sample point, you want to test that sample that you're going to be jar testing for both filtered and unfiltered P. And then the filter P, that's your baseline. That's how much you want to remove based on the filter P minus the plant's effluent target. Dose the jars according to plan. Usually 20 minutes of mixing is sufficient, 10 minutes of settling. And usually the settling is more than it's primarily a visual thing, because what you'll then do is you will basically remove the supernatant from the jars and run it through a 0.45 micron filter to test for soluble phosphorus. So really what you're doing is evaluating the efficacy of different coagulants at various molar ratios for soluble phosphorus reduction. Some basic calculations. So if you had a 1.5 mgd plant with 8 ppm of phosphorus or orthophosphate on the influent and a discharge limit of 1 ppm, your desired P reduction would be 7 plus parts of soluble phosphorus. Now, brings up another interesting point here in that, if a plant has a limit of 1, where do they really want to control that? Some plants will control at 0.8. Some plants like to be lower because of fluctuations in their influent or their chemical feed system, or, and they like to have that buffer. So an important question to ask is, if they're currently treating, is where do you like to control that effluent phosphorus number? And typically when I start jar testing, I'll start with looking at the coagulants all at a 2-to-1 molar ratio, aluminum to phosphorus. And then from there, can I go lower or do I have to go higher? So the first thing you want to do is determine how much P, to quantify the P that you want to remove. So you take the flow at 1.5 mgd times the 7 plus ppm, and then the density of water, and you get 88 pounds per day of phosphorus that you need to remove to achieve compliance. So how much aluminum do you need to remove those 88 pounds of phosphorus? So you would take the atomic weight, ratio of aluminum to phosphorus, times that molar ratio of 2, times the 88 pounds to get 153 pounds of aluminum that you'll need to remove 88 pounds of P. Now, this specific example said, okay, well, all right, so I've chosen sodium aluminate as my coagulant. And how much sodium aluminate am I going to need to feed to get 153 pounds of aluminum. So essentially, you take the 88 pounds and you divide it by the density of sodium aluminate, which is 12.3 pounds per gallon, and it's 10.6% aluminum, and you'll get 117 gallons a day of 38% sodium aluminate to deliver the 153 pounds of aluminum that you need. We kind of touched on this earlier. Some common feed points are the best feed point is post aeration right before secondary clarification. Also, I guess you want to feed the products neat. You really don't want to use carrier water if you don't have to. I've seen instances where if that carrier water is city water that has phosphorus in it, that there's a reaction there. So you really don't want to use carrier water. And also, again, account for all the phosphorus. Is there recycle streams from pressing sludge? And I guess the last important point is mixing again is critical for HMO formation. And I think with that, I'll hand it back to Chris Lacey.
All right. Thanks, Chris. Kick this over to the last slide. All right. So let's go ahead and open it up for questions. Please email any of those here to webinar@usalco.com. And if you'd like a copy again of the deck today, please also send that to webinar@usalco.com. Now let me go ahead and see what we got that's already come in. So, all right. So the first one, how does rare earth factor into treatment? So for phosphorus control.
Yeah, that's a great question. And it goes back to what I was mentioning about trying to get remove phosphorus below 0.3 ppm and the molar ratio, skyrocketing below that point. That's where rare earth metals can be useful. I know I've seen some applications where you're trying to use rare earth with conventional limits. When I mean conventional, 1 ppm or 0.6 ppm, they're really not cost effective in that range. They become more useful when you get below 3.3 ppm. And I've seen some facilities that will use aluminum and rare earth in conjunction with one another.
Okay.
And one other thing too, my understanding too, that's a material that's made overseas for the most part, if I'm not mistaken, or imported, I should say, and that could factor in. The cost and the supply chain could be a factor there as well.
Okay, cool. Thank you, Chris. All right. So also, would adding a DADMAC with alum help with phosphorus removal? Would adding a DADMAC with alum help?
I haven't seen where an alum. Well, if you're talking about a blend or if you're talking about two chemicals, it could facilitate better settling, but I don't think it would improve the phosphorus removal. In fact, if you had a blend, you would have less aluminum in the blend than you would have in straight alum. So you would end up feeding more of the blend just to get enough metal to react with the phosphorus you need, or to react with the phosphorus reduction you need. So I haven't really seen too much of that. And in those instances as well, if again, that's where the pack products, I think, can do a job with phosphorus removal, but also facilitate better settling and et cetera. I mean, I would say I would use a pack product before I would consider using an alum polymer blend if you were looking at settling, but it shouldn't really impact the phosphorus removal.
Okay. Sounds all right. Thank you. So looks like we have another. How does the different compositions, industrial versus municipal, affect the performance of coagulants? So I guess the different compositions of the water probably coming in of the influent.
Yeah, I think that speaks to what I mentioned earlier. I've seen ACH blends, ACH pack blends work really well in industrial water treatment, not only to facilitate phosphorus removal, but to remove all the constituents I mentioned earlier. But typically in muni applications, you've got a variety of products that will work from alum to pack, but the sweet spot seems to be in muni wastewater treatment, excuse me. The sweet spot seems to be the packs that are like 40% basicity, 17% aluminum oxide. They seem to work the best.
Okay. It looks like we're at our last one here. So how do stricter future regulations impact the phosphorus removal process and coagulant selection?
I've seen some plants limits be reduced from 1 to 0.6, and I still think that's manageable with conventional aluminum or iron-based coagulants. I guess if you get into those areas where the limits are below that, like in Wisconsin, I think the Chesapeake Bay has lower limits, then I guess it goes back to what I was saying about getting below 0.3, and you're just going to have to feed a heck of a lot more. Not to say you can't get there, not to say you can't get from 0.3 or 0.35 to 0.2, but once you hit that threshold, you're going to start to use a lot more coagulant, a lot more aluminum or iron-based coagulant. I mean, the efficacy will still be there, but at a much higher molar ratio.
Got it. Well, thank you, Chris. Thank you so much for helping us out with this webinar today and joining us. This is very valuable. Appreciate it. On behalf of the marketing team here at USALCO. And thank you all for joining us today. We will be posting this on YouTube for distribution later. It'll also be on LinkedIn, so you can find it that way as well. Well, thank you all. We'll hopefully see you again soon. Bye-bye.
Take care.